Okay, so Raph Bendahan-West is going to talk to us about dust segregation in HD21997. Take it away.
Yes.
And he's from Exeter.
Can people hear me? Yes? Cool. Works well. And this works. Okay, so hi everyone. I'm Raphael Bendahan-West. I'm a PhD student working at the University of Exeter with Seba Marino. And today I'll be talking to you about a way of constraining the origin of gas and debris disks using JWST and ALMA observations. So earlier today, Christine gave us a really nice talk about the introduction of debris disks, so I don't really have to go through this. But what we can recall from this is that debris disks can be observed in different ways. We can observe the thermal emission of our dust grains at sub-millimeter and millimeter wavelengths with facilities like ALMA. But we can also look at the scattered light emission of our disks at shorter wavelengths. Here I'm showing examples with SPHERE and GPI, but from previous talks we could actually add JWST here. Ultimately, what we're doing here with those different methods is we're tracing different grain sizes, with ALMA being tracing our large millimeter dust grains and our scattered light observations tracing our smaller dust grains. Although our large and small grains come from the same parent population of planetesimals, they behave differently dynamically. So if we look at the two main forces that are going to govern the dust dynamics, we know that both our small and large grains are going to feel gravity, but when it comes to outward forces like radiation pressure, only our small grains are going to be affected by this. And so this leads to our small grains actually being shifted outwards by a few percent compared to our larger grains. And so this can also be seen in this small plot here where we have our peak density of grains as a function of grain sizes where, again, our small grains are shifted outwards compared to our larger grains. And typically, we use this term beta to evaluate this ratio of our outward and inward forces. And so this defines how bound an object is to the disk, but at the same time, it also sets how slow or fast the dust rotates relative to coherent velocity. And so I've been talking about the dust dynamics, but also from Christine's talk, we know that debris disks can have gas. So gaseous debris disks are mostly found around young A-type stars, and in terms of observing this gas, we typically look for CO. And so this has been done previously by looking for different CO isotopes, like 12CO and 13CO with ALMA. But also just recently, we also managed to resolve the gas with JWST. However, the origin of gas in debris disks is still highly debated. And so we typically have those two pictures where our gas could be of primordial origin, where it is leftover gas from the protoplanetary disk phase and is typically hydrogen-dominated, or you can be in a secondary gas origin phase where your gas is going to be released by planetesimal collisions and is typically hydrogen-poor and CO-dominated. Distinguishing between those two scenarios is actually quite complicated because it's quite hard to detect or constrain your hydrogen levels. So we need alternative ways to constrain the gas origin in these systems, and this is what I'll be talking to you about today. So for this, I'm focusing on this gas-rich debris disk that is around a young A-type star called HD21997. In terms of past observations, they actually trace back from more than a decade ago now, and we have ALMA dust and gas observations of this system. But in terms of scattered light detection, there's none previously done, and this is until JWST. And so here on the left, I'm showing you some new ALMA observations, but most importantly on the right here, I'm showing you first scattered light observations of this system thanks to JWST, where we actually managed to detect the disk with MIRI and NIRCam chronography at 11.4 micron and 2 micron. So from this, we can forward model our JWST disk. So here I'm showing you an example of our 2 micron data, where we model the disk and try and constrain the scattered light disk parameters for the first time. From this, then, we can subtract our disk, and we can check for any asymmetries in the disk, which we don't see any, or we can check whether there are any companions that were hidden behind the emission of the disk, which we don't find any typical. Okay, so from our best fit models, we see that our peak surface density for our small grains is around 150 AU, and this matches quite well with our azimuthally average radial profiles for our NIRCam and MIRI observations. And we can basically do the same thing for our ALMA observations as well, and we find that our peak radius is actually at 90 AU. And so instantly from comparing our ALMA and JWST observations, we're seeing that our small grains are peaking 60 AU outwards compared to our large grains. And if we recall my introductory slides on dust dynamics, we know that our small grains are expected to be shifted outwards compared to our large grains. However, here on the left, I'm showing you two examples of what this typical shift between our large grains and small grains should look like. And this is just typically a few percent, and it's quite different compared to our large 65% shift. So the first question is, what is going on here? What is different? And so in the examples that I'm showing here on the left, and the difference is compared to our observation is that we also have gas in our system. And now if we look at examples of gas-rich debris disk, and we do the same exercise of comparing our large grains and small grains, we're seeing that the shift is now not just a few percent, but tens of percent, which matches a lot better with what we're looking at. Okay, so what is going on in terms of dynamics? And for this, we can bring back our dust dynamic picture, where we had our beta that sets how slow or fast our dust rotates, and then we can add our gas to this, and we can see how the gas affects our classical dust dynamic picture. And so this actually, the gas drags in or pushes outwards dust grains depending on the relative velocity between the gas and the dust, where the gas rotational velocity is governed by the local pressure gradient and can be described as so here. And we can see that instead of having a beta like we have for the dust, we have an eta, and this eta sets how fast or slow the gas rotates relative to Keplerian motion. And so we can look at our different relative velocity scenarios by comparing our eta and our beta. And so in a case where eta is going to be smaller than beta, then our gas is going to be rotating faster than the dust, and our dust is going to be pushed outwards. Alternatively, if our eta is bigger than our beta, then our gas is going to be rotating slower than the dust, and our dust is going to be dragged inwards. And so what's interesting now is to know when actually this dust gets dragged inwards and when does it get pushed away. And so we can take this example of this Gaussian gas surface density profile, and we can first focus on the right side of it, where we have a negative pressure gradient, which means that our eta is positive, which means that our gas is going to be sub-Keplerian. To this, we can bring our large and small grains, and we can first focus on our large grains. And so for our large grains, we have a small value for beta, which means that we're in a regime where eta is going to be bigger than beta. And this means that our gas is going to rotate slower than the dust, and our large grains are going to be dragged inwards. When it comes to the small grains, we have a bigger beta value, and we're actually in a regime where our eta is smaller than beta, which means that once again that our gas rotates faster than the dust, and our small grains are going to be pushed outwards. If we look on the other side, we have a positive pressure gradient, our eta is negative, and for both our dust grains, our beta is always going to be positive. So we're always going to be in a regime where our gas is going to be rotating faster than the dust, and both our dust grains are going to be pushed outwards. So over time, what happens is our dust grains are going to migrate to a location where eta is going to be equals to beta, and for our large grains, this happens to be at the pressure maximum. But for our small grains, this happens to be at the outer edge of a gas disk, explaining our overall increase in outward migration for our smaller grains. Okay, and so finally what we can do is we can use the relative velocities between our gas and our dust with our beta and eta, and we can see how long it takes for our dust grains to migrate, and we can constrain this as a function of gas surface density. So we can calculate this for our small grains that have been shifted outward by 60 AU. And to this, we can add some time constraints, such as the age of the system, because we're requiring our small grains to have migrated before, like in a time shorter than the age of the system. But more importantly, more constraining is that we're requiring our small grains to have migrated before they get destroyed. So we need our migration timescale to be actually smaller than our dust collisional lifetime for our small grains, and which means that we can now rule out the regions of parameter space in red, where our dust actually gets destroyed before migrating the 60 AU shift that we've observed. So then this leaves us with this valid parameter space that we have now in green, which, well, it's not working, oh yeah, which now constrains our gas surface density that is required for small grains to be observed 60% outwards. And now we can bring back our question of gas origin, and to this plot we can add different regions for the gas surface density for different gas origins, and we can start evaluating the overlap region between our valid parameter space in green and our CO-dominated and hydrogen-dominated scenarios. In this exact case, we can't pinpoint exactly a preferred gas origin scenario. However, what will be really interesting is seeing what the intermediate size grains are, how they are actually behaving. If they're behaving like the small grains and are shifted outwards, or if they're behaving like the large grains and are co-located with them, or even something in between. And so this will help us constrain the required gas surface density by using those same dust migration models, and ultimately we'll be able to pinpoint the gas origin in this system. Okay, I've got 1 minute to spare. I can go through my summary. Cool. So we saw that gaseous debris disks exist primarily around young A-type stars. However, the gas origins is uncertain and quite hard to determine. I showed you first scattered light detections of this system HD21997, where we see our small grains to be shifted 68U outwards compared to our large grains. And this can only be possible when we have this synergy between ALMA, which is going to look at our large grains, and JWST or other instruments that can look at the scattered light. And we saw that the gas can actually push the small grains further out and a little bit further than radiation pressure alone, and we can use the dust grain migration timescale to constrain the required gas surface density. But ultimately what we need is more information about what the intermediate size grains are going to do so that we can constrain better the origin of gas in these systems. Thank you for listening.
Thank you, Raph. Do we have questions from the audience? There's one over here.
It's a great talk. I'm sorry, you mentioned this very briefly about looking for hidden companions. I mean, that wasn't the purpose of your talk so much, but I think every single major survey from the ground has tried to look for a planet around this star and has failed. Do you have any insights, especially because I think this star has a proper motion anomaly that's marginally significant, so there might be something there.
Yes, so we did the exercise of trying to look for planets and then using those detection probability maps to quantify the sensitivity we were to planets. And like you say, this one also has strong proper motion anomaly. Yes, so in this system, actually, we can rule out most of the parameter space that is closer to the inner edge of a disk and further out. And so we actually, so just by looking at the proper motion anomaly information, we're expecting a companion to be in those inner regions as well, complicating the picture even more.
Thanks. Another question up here? Yeah.
Nice talk, Eric Gaidos, University of Hawaii. How strongly does your model depend on the assumption that the gas and dust start off co-located? So I can cook up an extreme scenario, of course, with a debris disk where you have just some gas somewhere, and then there's dust production, which has nothing to do with the gas.
Yes, so these models depend a lot on the gas surface, surface density profile. So it's really going to depend where your gas outer edge is going to be. So if it's not co-located with your large grains, then I guess that opens another can of worms, right? But that can also tell you where the gas comes from just by looking at whether the gas is co-located or not with the large grains, like you were saying. So yes, our models just depend a lot on the eta value, which is going to depend a lot on your gas surface density profile.
Don't get me wrong, it's very elegant, clever.
Thank you.
Okay, any other question? Any question online? No question online. Raph, thank you very much for your talk, a very interesting object. Thank you.